talk of the afternoon session before we have these panel discussions is by Cho from Queen Mary College of the University of London, and the title is Magnetohydrodynamic Shallow Water Turbulence on the Sphere.
Okay, thank you for inviting me, the organizers. So this talk can be considered essentially an extension or continuation of two talks today that you've already heard, one by Richard Scott and one, of course, by Steve Tobias. And I'll give you the upshot. I mean, the point I'm going to make in the talk is essentially identical to Steve's, in that with magnetic field, the zonal flows that you typically see in hydrodynamic flows go away. Okay, so this is a work that's very much in progress, and I should mention that it's a collaborative work with an undergrad, Erica Staling, who's now a graduate student at Princeton, working with Jeff, I think, right? Okay, so here's the outline of the talk. First, I'll go through a little bit of MHD definitions and equations. It may not be familiar to some of you at least. And then give you some examples with comparison with hydro with weak magnetic fields. And I'll quantify what I mean by weak shortly. And then go on to contrast that with behavior with strong magnetic fields. Since I'm in the astronomy department, I have to do some application work. So let me just show you two simple applications of the MHD shallow water turbulence model, and then conclude the talk. Okay, so what's motivating this work is, of course, to try and explore the full parameter space for MHD shallow water turbulence. That work has not been done yet. So from an applied mathematics point of view, it's something we want to investigate. In particular, we want to look at the emergence and evolution of physical structures, normal hydrodynamic vortices, jets, and of course there are magnetic vortices, which I'll show later. And then the behavior in spectral space when you add the magnetic field to the problem. The particular application to astronomy is, of course, to look at things like the solar tachycline, which is what you heard about this afternoon. And in particular, I've been lately looking at trying to study atmospheric circulation on extrasolar giant planets. These are planets discovered outside of our solar system. And there are other applications, such as looking at flows on giant stars, which are radiatively stratified on the outside, much like planets, and flows on neutron stars and white dwarfs. Okay, so what's a magnetofluid? First of all, it's a plasma. So in order to be a plasma, you have to meet a few basic criteria. One is quasi-neutrality, which means that the length scale that you want to look at should be much larger than the Debye length, this lambda d. Debye length is just the screening length for two charges in a plasma. So it's very much like the deformation radius for pure vortex dynamics problems. Second is the so-called plasma parameter. There are other plasma parameters that's going to come up later, and I'll try to distinguish so you don't get confused. Basically, this thing just says that there ought to be enough particles inside the screening length so that there are enough collisions to actually have the fluid act like have the plasma act like a fluid. And thirdly, that the plasma frequency should be also much greater than any of the neutral frequencies. So remember, plasma frequency for the systems that we're interested in are on the order of millisecond to even microseconds. So they're incredibly fast compared to any of the normal atmospheric modes that we want to look at. And down here are just, okay, if that defines a plasma, this is sort of what would define MHD regime for the plasma. that is the characteristic length scale should be much greater than the mean free path and the gyro radius, and the conductivity has to be essentially infinite. Okay, so that you can use idealized Ohm's law. And finally, any sort of effective characteristic speed in the problem should be much less than, of course, the speed of light. All right, I won't dwell too much on the equations. It should be all familiar to everyone here. What's written down is, of course, the shallow water equation. And it's fairly simple to magnetize the equations. And all that really means is just adding this Lorentz force term to the momentum equation, and it gets 2 extra scalar equation, or 1 vector equation. Okay. This set of equations was basically first derived, or at least appeared in print in a paper by Gilman in Astrophysical Journal in 2000. Important thing to remember here is it is a MHD fluid, which means any magnetic field in the fluid is quote-unquote frozen into the fluid. So it just follows what the fluid does. Just a quick word about previous MHD work. You heard about Steve's work, which is this afternoon, which is a pure 2-dimensional, meaning non-divergent on the beta plane. And then there's some shallow water MHD work, but these have been pretty much limited to studying wave dispersions or stability. That is, there's no shallow water turbulence work done so far. Actually, we've gone slightly ahead of the, or more advanced of the shallow water equation. That is, we're interested in looking at one-layer equations with horizontally varying temperature structure or thermal structure. So we've actually derived, much like Salvi and Ripa did, what's called the equivalent barotropic equations. All that is you allow for outcropping of one thermodynamic variable on the bottom surface. So here's the picture. So you can actually represent thermodynamics within the context of one-layer equation. So you couple the thermodynamics back into the equation. That basically means just having one more equation. So you're no longer, now for the hydro case, solving just 3 equations, but 4 equations. So really the only difference is that extra equation and this little thermodynamic factor in your H equation. Now, the way I've written it here, your H could be temperature or pressure on the isentrope here. So when K is equal to 1 and theta is a constant, the whole thing just reduces to your normal shallow water equation. Okay. So a little bit about the actual engineering part of this. We're solving the equation using pseudospectral with hyperviscosity. And if you actually write the equation down in vorticity, divergence, and current and charge form, so the current would be the curl of the magnetic field. Yes, do you have the question?
James, that theta, the third equation is not coupled to any of the others. There's no theta naught anywhere else.
Theta in the equation. Ripa's equation, theta is in the equation too.
Yeah, there are actually several forms of this one layer with inhomogeneous temperature structure.
But it's
So,
completely decoupled.
yes.
There's theta naught in the
Kappa
other
comes from
equation.
the H term should have an H over theta.
Yeah,
First
it's
line.
actually it's embedded in H.
H is,
H is not your mass field.
so H in the first equation is different from H in the second equation.
Yeah, that's why I put a little G star. So there are extra terms if you want to actually properly solve the whole set. Okay. Okay. So the trick is to use the current charge form, which is the curve of the B field and the divergence of the V field. When you do that, the normal way of solving the shallow water equation using the pseudoscalars in pseudospectral method can be carried right over. So it's actually a fairly easy work that an undergrad can do actually. Right. And the calculation I'm going to show in this talk it ranges from T85 to T213. It's not massive by today's standards, but we were interested in exploring the parameter space, so we don't need to go at massive calculations right now anyway. Initial conditions. Both V and B fields are random initially. These are decaying experiments, freely evolving, and they're nonlinearly balanced so that we try to suppress appearance of magnetogravity waves in the problem. That's something we want to look at more carefully in the future. Just a list of things you should keep in mind. Some important conserved quantities and parameters that I'll be talking about in the talk. Energy and entropy for hydro case, for the magnetic part, especially if you're in the pure 2D regime, you have magnetic potential that's conserved, the cross helicity. And for shallow water, we define the Froude number this way. And an important parameter that I'll be talking about a lot is the plasma or magnetic beta. Now, this isn't the magnetic beta, the same magnetic beta that Steve Tobias mentioned. It's some sort of shallow water analog of the real plasma beta. And it's just a measure of your height or pressure analog in shallow water to the magnetic energy, okay? Where the magnetic field is just scaled by the Alfvén speed. Okay, some results. This is what you're seeing is the spectral space and physical space picture for the large beta plasma beta case, meaning the magnetic field is weak. So they go inverse, right? Large beta means weak field, small beta means very strong magnetic field. And time goes downward. I don't know if you can see it. It's roughly 2 decades of spectrum here. And there's nothing new here. You basically see what you've always seen in turbulent simulations. You start at more or less high wave numbers, and you have inverse cascade. Initially, you have a fairly shallow spectrum, particularly on the high wave number side. But as you get more and more coherent structures, your spectrum steepens. Nothing new there. Small magnetic field does not change anything. Now, since we're doing shallow water, you can also vary the Froude number. And again, at small or weak magnetic field, there's no difference between your good old normal shallow water hydro case. What you're seeing here is with no rotation, the vorticity field, and left is Froude number small, and right side is Froude number more 1, right? And the main difference is, of course, for more 2D-like case, you have very nearly circular, nice-looking vortices, whereas when the Froude number gets bigger, your vortices tend to get more blobby. And the inverse cascade is muted. And this is all seen, I think at first by Provani et al. In '94 chaos paper. Right, so again, nothing new there. So what happens if you now start to ramp up the magnetic field in the simulation? So we're still at the no rotation case, so that you can clearly see the difference. what happens is increasing the magnetic field inhibits inverse cascade. You can clearly see that when you plot out the spectrum. I don't show it here, but basically there's not much inverse cascade, and the spectrum at later times look more or less like the initial spectrum, slightly more broadened. Instead, the magnetic potential, A, which is defined as the, such that B is the curl of A, that quantity inverse cascades. But of course, this field doesn't couple to the rotation. So that's one clue to why we're not getting any zonal flows. As I show more examples in a high B field case. Okay, so you could see it here, the comparison. When the B field is low, remember this is in real units 600 Gauss. Earth is like half a Gauss, so this is still not that small. But what happens is you still get more or less hydro-like case, and the magnetic field just more or less follows the vorticity field. But if you now increase the V field such that it's 100 times greater, you almost get a reversing between the vorticity and the current. That is, you get magnetic vortices. You don't get any of these sort of sheet-like structures in the current field. Remember, this is the curl of the curl of the magnetic field. You get the more current stringy-like structure in the vorticity field. Okay. Okay. Now we put everything allowed in the MHD shallow water model, including rotation and B field, and see how those two things couple. And you can now clearly see what's going on. Low magnetic field, again, you get the same thing you've seen in hydro case. You've seen lots of these pictures today. Here's a zonal wind plot corresponding to this case. This is the eastward wind averaged over longitude as a function of latitude. I think it's more or less like Jupiter parameters. You get multiple jets. Right? But take the exact same case and add strong initial magnetic field, and as you can see, the jets go away. Okay. You can also tell from the potential vorticity plot here that we're looking at a fairly QG regime. Okay. The lines are fairly circular. Okay, so just quickly run through a couple of simple applications of the model. Steve talked about the question of tachocline. Why is it there? Why isn't it gone away? Actually, I've been kind of approaching the problem in slightly different but related direction. And that is, if you look at the radiative core of the sun, there is no differential rotation. It rotates like a solid body, and I was interested in how that comes about. And one thing we tried to do was, within the context of the simple shallow water model, what if you actually tried to plug in your best guess at the parameters that go into the shallow water model? And these are a set of parameters for the tachocline regime. Of course, for that regime, starting again the exact same way, initial random conditions, you in fact get solid body rotation because there's no zonal jets forming. But if you now move away from the tachocline and look at the photosphere, the surface of the sun, where there is in fact another stable layer, then of course there we have the angular rotation profile. It's very well measured, especially between minus 60 and 60 degrees. And if you put that parameter in, of course at the surface the magnetic field is much weaker because it's a dipole field, primarily dipole field. So there you get your zonal wind, and occur. Okay, this is a simple calculation, but you could sort of plausibly argue that the reason why you're seeing shear between the photospheric layer and the tychocline layer might be simply because of the strength of the magnetic field. You see? Okay. By the way, this is the magnetic current or the divergence of the B field that you're seeing, and I thought it was kind of interesting that at least at this level of crappy simulation, you can maybe draw a parallel. Okay, so that's kind of interesting. So we're talking about the magnetic field as a divergence of the B field or the convergence at various points. And isn't it interesting that they also tend to come in pairs? Okay. All right. For the more meaty part, as I said, the problem I've been interested in lately is looking at flows on giant planets, not in our solar system, but outside of our solar system. There are over 300 of these guys now. Okay, most are Jupiter-like. Some are maybe Neptune-like, even down to Earth-like planets. So far, most of these planets are found to orbit very close in to their host stars. Okay, much closer than 5AU, which is where our current Jupiter is. There are lots of ideas about how that might happen. I won't get into that here, but it's suffice to point out that many of these, maybe more than a quarter of these, are extremely close in to their host stars. So we're talking about planets that are not 100 or 200 degrees, but 2,000, maybe 3,000 degrees, so super, extremely hot. And some of them are probably tidally locked, which means that their rotation rates are synchronized with their orbit. So if you can figure out what their orbits are, you can actually infer their rotation rate, which is one of the most important dynamical parameters. Right? We can't get that directly. We can only infer that from orbital information. But it's possible to get it. Just to sort of give you a comparison, this is for a calculation for one of those extrasolar giant planets, a close-in one, without the magnetic field. What you've seen is potential vorticity. This is although I said I was only going to talk about lowish res calculations, this is a massive one, as you can probably tell. I think this is T341. Okay. Hyperviscosity. But what I want to point out is with these physical parameters, in other words, the Rhine scales are roughly about the size of the planet, so it's the deformation radius. Basically, what you see is formation of very strong cyclonic circumpolar vortices, which are usually off the pole, okay, off center. And you can, if you can read PV plots, this corresponds to roughly 2 or 3 broad jets. Okay, they're not as steady as our normal solar system Jupiter ones, but Richard talked about also seeing very robust cyclonic vortices. I think this is just a normal outcome of PV conservation. So, and I want to point out that usually the presence and also the strength is very sensitively related to the deformation radius. So larger deformation radius, stronger the vortices, but they can be more off the pole. Right? So if you're looking at very small deformation radius cases, you may not get those polar vortices forming. They may not get a chance to form. 1 minute. Okay. So just to give you context, because we're talking about MHD modeling, here this is for the Earth, but basically all of us have been talking about this area, or even below if you're talking about oceans. But of course, the upper part of the atmosphere is ionized. And for exoplanets, we're talking about, because of their close proximity to their parent stars, more than 5,000 times the flux, the short-wave components. So even if you couldn't quite exactly quantify because of technicalities or lack of observation, you could still plausibly argue that the Chapman layer on the planets will probably extend much further down on the extrasolar planets. Of course, because they are getting irradiated, there's a huge radiative layer, huge compared to solar system planets, and paradoxically, that area probably won't be ionized. Okay. Okay. Let me just quickly skip this. All right, and just get to the main point. So, just as a quick test, I'm sorry, I'm plotting vorticity here instead of PV because I want to point out the alternating bands, but I should be plotting PV. But then again, as we commented on earlier, for the MHD shallow water system, there is no potential vorticity analog. Okay, there's no conserved quantity like a potential vorticity that at least I know of. So maybe it's pointless to even plot PV at that point. But anyway, what you're seeing is the set of simulations with beta scale very small, deformation scale also very small, but everything same except the plasma beta parameter ranging from infinity, i.e. no magnetic field, and down. And Steve pointed out that even a very small magnetic field tends to disrupt the jets. Certainly, the jets are starting to go away at this point. Then, of course, at about order 1, it really completely goes away. Okay, those are the zonal winds. But if you now track it against the current, the curl of the magnetic field, so you clearly see what's going on. Of course, this is blank because there's no magnetic field. But here, you get sheet-like structure for the current, and it seems to be just following the flow. But at somewhere at this point, and it's a fairly sharp transition, what happens is you get magnetic vorticity, and then I argue that actually the vorticity is tracking the magnetic field, not the other way around. Okay, and because the magnetic potential is what's cascading backwards, what happens is if you wait long enough, these vortices just get bigger and bigger and bigger. Okay, there's no sort of characteristic scale which they stop growing. Okay. All right. So I think I only have a few minutes, or maybe 1 minute. So just show and tell what's going on currently. We're trying to better quantify the relationship between the ion density and characteristic magnetic field within the context of this model. It's fairly tricky, actually. It turns out, there are lots of unknowns. Certainly, this involves knowing chemistry, which I don't know anything about. We want to also look at introducing strong external, particularly dipole field on these things. And our idea is maybe, again, within the context of one-layer modeling, treat the dipole field like a permanent divergence source and sink. Okay, that's probably the most reasonable thing to do, well, with a simple model like this. And of course, there are all these additional complicating factors on real planets. For example, there's tidal locking or tidal synchronization on these planets. which means only half of the atmosphere is ionized, the other half is neutral. Of course, we haven't even really talked about migrating ionization dependencies. And then a problem that I'm particularly interested in is the coupling between the neutral atmosphere and the ionized atmosphere. So that introduces a whole host of new physics, and that probably that means we will have to go to a two-layer model. So let me just conclude at this point. What I want to say is it's necessary to consider MHD effects coupled with rotation and stratification when modeling almost all astrophysical objects. Hence, why I guess why I'm here at this meeting. Atmosphere of many extrasolar giant planets should be fairly strongly ionized. Sorry? Okay. And there seems to be a fairly distinct transition between, what I call low and high magnetic field regimes. Okay. At high magnetic field strength, the flow is dominated by current spikes or, magnetic charges. Now remember, in the shallow water system, the divergence of B is not equal to 0, as it would be in a 3D Maxwell's equation. Right? It's just the exact analog of horizontal divergence, velocity divergence, going from pure 2D to shallow water system. So you see current spikes rather than sheets, and it's magnetic vortex dominated. And concurrent with that, you don't see any zonal jets forming. Okay. So it's a complete different dynamic at work. So it's as if the fluid is frozen into the magnetic field, not the other way around. Thank you very much.
Let me ask a question. Jupiter has a fairly strong magnetic field. Why are there jets on Jupiter?
The magnetic field, where the magnetic field really comes into play would be at much higher altitude than where you're seeing the zonal jets, in all the tops today. So it's much further down.
The magnetic field is further down? Or
No.
Further up?
The ionization, level of ionization.
Oh, so you need a certain level of ionization. That's the secret. Any other questions? Sorry, Michael. No, let's go to Michael first.
Just to clarify, could we have the picture of your last run again? You had these big elliptical-looking structures on the right, yeah.
On the right.
Yeah, on the two right-hand pictures, for instance.
Yes.
You're plotting vorticity. Oh, that's current. The bottom one's current.
Right. That's the
So
curve.
it's saying the field lines are following the contours of vorticity. The field lines are just circular. Okay, and that's.
I would like to say the other way, actually, but yes.
That's why they can survive. They keep spinning because they're fully wound up and they've line reconnected and can't. It isn't like a watch spring anymore.
Right.
Okay, I think.
Yeah.
I have a very basic question.
Fire away.
Okay, when you have shallow water with this free surface, okay, normally we know how we deduce this model, and basically pressure is 0 on the surface. What about magnetic pressure? Am I correct that magnetic pressure drops on the surface of your shallow water?
Yeah.
When something is it safe to do that?
I think to the level of approximation of shallow water, I think it's okay. That's actually a very subtle issue, and I'm not sure. You can.
Just to rephrase the question, what is the fundamental derivation of magnetic shallow water equations?
Oh, so basically it's the same as the hydro part. That is the aspect ratio for the scale of the magnetic field is very small. So the horizontal extent is much larger than the vertical extent.
There's a problem about where the current goes, isn't there? If the current's coming out of the screen, where does it go back? How does it loop around.
It doesn't loop around. There's as you know, as Steve was saying, the magnetic field is in the layer, and the current comes out and in both directions, right? Plus or minus current.
That's my question. The current
Yeah.
has to go somewhere. Div J is 0 if you have charge neutrality.
No. In 3D case, you would have to have that thing loop around, but in 2D you don't.
It's just infinite. Current goes to heaven and down to
Sure.
It's like vortex lines in 2D.
Yeah, the hypothesis of infinite conductivity, which is kind of,
Vortex lines just go on.
you're right. I mean, you're
Well,
doing
Well,
the same equation.
that's a normal MHD.
No, I know, but it's
approximation.
strange physically.
Plasmas are a pretty good approximation of perfect conductors.
Okay.
That's an approximation I feel pretty safe.
I was thinking myself it's more a trick to be able actually to not to have to compute the magnetic field very far away. I was thinking it was more a trick to do that.
If I'm correct, Paul Deller has derived these MHD equations with the REPA term in great detail. I think it's all in physics of plasmas.
I know the work. but,
2000 to 2003 or something like that. So,
Yeah, I'm aware of the work, but
Okay.
Yeah. it's not-
now, can we get a organizer of the meeting to tell us what happens next? And before we do that, can we thank the speaker?